So this talk is called Crypto No. So we're going to talk a little about some issues that I've seen doing some crypto review and some of our stuff at NM, and a few other entertaining things. So a little bit about me: lead for penetration testing and vulnerability management at Northwestern Mutual. Previously managed pen testing at Sickich and 403 Labs, and before that did a bunch of things at Metavante, now known as FIS. So your general disclaimer that presentation represents my personal opinions, and I make comments that don't directly reflect the official position of NM. So crypto, right? So we've been working with a lot of folks lately that are really wanting to do the right thing. They want to protect data, and this is what they think they implement. And they've chosen the right ciphers. They've done a lot of really good things, but at the end of the day, some really simple flaws can sometimes make your crypto really more like this. So, familiar with any sort of encryption, you might recognize this. This is actually running an image like a PNG through AES ECB. So there's lots of artifacts, lots of traces that somebody can actually exploit or try to dig data on. So here's our agenda. So we're going to talk very briefly about Cypher Recommendations, and then we're going to get to some threat modeling, look at a couple different case studies. That's the actual code. I'll try to do my best to make the biggest that I can, and you can actually read it. Talk a little bit about key management and just some general recommendations. So this is it. This is all I'm going to say for recommendations for Cypher Suites. There's actually a really good post by Thomas Tasek. He used to run Monsanto and their crypto analysis services. He recently posted what are the cryptographic right answers for 2018. I recommend going and reading this. And I'm not going to dive into one mode versus another mode. So if you have a need, please go read that paper and then apply the rest of what we're going to talk about to that. So lately, everybody's been talking about, encryption and should encrypt all the things. And what we've realized is that for a lot of cases, that's probably the right thing, but may not always be the right thing. You definitely have some trade-offs between performance when we start encrypting everything. You also have trade-offs between visibility if you're from a security mindset, and need to look at, say, network traffic. And so there may be different needs depending on what's actually going on. And so we're going to use a really basic model to kind of talk about encryption and where it might have benefit and where it may not. So this is our really basic web app, right? So you've got a user, they're going to connect you to the internet. It's some sort of application. Imagine this is either an API or just a basic web app. Maybe it's some crappy PHP app, whatever app it might be that connects to some sort of database. Could be whatever, SQL Server, MySQL. And then ultimately that has to store data somewhere, right? So whether that's on a physical server or it's in the cloud on EBS volume or something like that, these are our general components that we're going to use here. So when you say encrypt all the things, well, what does that actually mean? Where are the different places that we can actually apply this encryption? So you could actually do some encryption in your browser. You could potentially do it at the application level. You could do it at the database level, maybe at the disk level. It could be, transportation along the way. That data has to move from one place to another place. And so you're sort of posed with the question of where should we encrypt, and how should that work? So one of the things that I think can be really useful in determining where do you actually need to encrypt and what makes the most sense is doing something called threat modeling. And it really helps inform what attacks are likely on the system, and it helps you make informed decisions about what you're actually trying to protect. So I really enjoy this graphic to describe threat modeling. I totally stole this from CyberSec Stu off of Twitter, and the way this is described, so if you're not familiar with threat modeling, is we're going to say that there's an asset, the person. The vulnerability is their balance on this tightrope, and the threat is these crocodiles down here, and the impact of that happening is him being eaten. So that's threat modeling in general, and we're going to take that sort of concept and apply that to these systems. So I'm assuming many of you have seen this CIA Triad. Bear with me for a second while I kind of explain some things to make this all make sense. So we've got, these are some of the main pillars for information security. So confidentiality, integrity, and availability. Two of these pieces play really well into encryption. So the confidentiality and integrity pieces. You'll see those used a lot to try to protect those. So jumping back to our threat modeling, what we're going to use here is a model called Stride. So Microsoft developed this model quite a few years ago. There's actually a really great book, creatively titled Threat Modeling, by Adam Shostak. So if you find this interesting, you think this is useful, please go read that book. It's got a lot of great information. We're only going to scratch the surface here. And they also have a really great card game, like actual card game you can go and play, to get you to creatively think about different threats that may occur against your systems. But tying that back to the CIA Triad, so you've got tampering and this thing's still line up. So you got tampering that ties to integrity, and information disclosure that ties to confidentiality. So if we're thinking that those two categories can be used to, or we can use encryption to help protect those two categories, as we start to do some of our threat modeling, we can see that where those threats or those threat categories show up, we can then see, does it make sense? Can encryption be an additional level of protection against those threats? So here we got the two main categories. So what we're going to do next is use a tool, again, creatively titled Microsoft Threat Modeling Tool. I think the latest version is 2016. It's a free download if you want to play with this and try this out. Switch over to the actual tool now. And so what you're able to do is, there we go. So basically what you end up with is on the right, they have all these different stencils. So you're able to pull those onto this sort of graph paper here. You tie those together with different forms of communication. So in our example, we're using HTTP, the web protocol, to tie the browser to a web server. And then there's a binary that we're using to assume that's maybe like the SQL Server protocol, or maybe it's a MySQL protocol to tie the web server to a SQL database. Now, one of the cool things about this tool is you can draw out your environment, kind of how you see it, and then you can have it basically run these threat models for you. If I can find my cursor here. And so now we went to analysis view. And so basically took all those components that we put together and said, okay, what are the potential threats against that? And we can see some common ones that you might assume are going to be there. So we're talking about a SQL database, so things like SQL injection show up. There's a bunch of different ones associated with denial of service. For our purposes of talk here, we're not concerned so much about like the availability aspects of things, but more about the confidentiality and integrity pieces. So what we can do is take this list now. I don't really feel like the tool is exhaustive necessarily in like all the different threats that it can think of. This is where sort of you as an analyst would have to think, what are all the other ones that are potentially there? And start to build out that list of threats. So this is a subset of the list that we just looked at. So we can see here there's a few different ones. We have some tampering, we have some denial of service, some elevation privilege, and information disclosure. So thinking to those different categories we said before would be a value for us to look at for encryption. We've got two here. So data flow sniffing, unencrypted HTTP, right? We can fix that with TLS. And we also have this other one for SQL injection as far as the tampering category goes. And there's some places that we can look at to do encryption that actually make it a lot harder for an attacker to gain access to that clear text data. So what we're going to do now is actually walk through like each of those subcomponents, talk about what sort of threats might be against each of those, and what are the use cases for kind of doing that type of stuff. So for the client-side encryption, so I kind of think of this as like in the browser. Like if you're trying to actually encrypt stuff in the browser, you're trying to prevent data theft or somebody else from seeing that data, right? You're trying to encrypt it as soon as you enter the data into the system and it gets sent off. Maybe you're trying to prevent a third-party software as a service from accessing it. Maybe you're trying to prevent that data even from your own systems from accessing it. We partnered with a company at NM when we do account aggregation. And one of the things that happens is when clients enter their credentials, they put into the site, and we don't want to see any of that data, right? We don't care what it is. We only care what those account values are. So when we actually do our account aggregation, we can help you see what your financial plans are. So one of the things we did a few years back is we partnered with this company to add a new feature so that we can do client-side encryption, bypassing any opportunity for us to actually look at any of that data, and then sends on to the actual company where they decrypt it with their private key, and then we're able to get some sort of response back that says, hey, all was good, and now we can see the data we want to see without having to see any of the really sensitive info. So it can be used as a risk mitigation tool. It's also used quite a bit in like secure messaging clients, things like Signal, and there's a bunch of other ones, as well as like cloud-based password managers. So if you don't want somebody else to see it, you probably should encrypt it before you send it. So the app server is probably the most common place that people do encryption. I feel like it's probably one of the better places to do it. It probably gains you the most by doing the encryption at this point. And there's a little icon here for an HSM, and we'll talk a little bit about that in a minute. But I also learned that HSM is really kind of an acronym for something else, like High School Musical. So when I tried to search for icons this morning for HSM, like something completely different came up that I was not expecting. And so one of the things I think is interesting about this is when you start to look about what threats does this actually protect against, there's database attacks, right? So if somebody's actually trying to attack the database, and you're not doing the decryption there, and you're doing decryption in another spot, they're not able to get that clear text data. So things like SQL injection, you can steal it, but you can't necessarily read it. A good example of that is the Adobe Breach from a few years ago, right? When that got released, you could see all the usernames, and you could see the encrypted passwords, which, by the way, you should not encrypt passwords. It's a bad practice. But you can tell that the encryption was done at the application layer. So even though the data was stolen, they weren't directly able to steal and use that data, right? Because it was done at the application layer. So they would have to have gotten access to the application and ultimately the keys to do the decryption. Other than it was in ECB and you can do all the attacks against it. So another thought here too is another threat might be administrative access. So if a server admin or DBA were to have full-blown access to, say, like database level encryption, they would be able to decrypt and analyze all the data. Whereas if you use something like an HSM, where it sort of abstracts that from the different administrators, they won't be able to have direct access to that data. So then we also have then database level encryption. So this one's interesting. We'll kind of get into that, but it can help protect against theft and accidental data exposure. I think there's some caveats to that. With database encryption, you generally have two forms, right? There's actually encrypting the columns themselves specifically with keys and key material. And there's another form called transparent data encryption. I don't know what the use of transparent data encryption is other than to do checkbox security. And I'll show you in a minute like an actual blog post from Microsoft that basically says that. And you may have the opportunity in case say a hard drive gets lost or stolen. Now the problem is if it's all one drive and you actually putting the keys on the drive as well as it's using for the data itself, then it's kind of useless. So I'm not a huge fan of it as far as database encryption goes. I'd much rather see things at the application tier. I think it offers more protection. And I was mentioning the transparent data encryption. And so Microsoft themselves highlights that enabling something like this in like SQL Server doesn't protect against things like SQL injection attacks. In fact, it doesn't even protect against anybody who has physical access to the OS or any sort of image. So like if you have VMware or VMDK or something like that, if you have that data, you basically have enough you need to reconstruct everything. So I'm not sure what this actually protects against, but it's an option. And then next you have the media level encryption. So this is, actually the bits getting written to some sort of media. So whether this is flash on a laptop or something spinning disk on a server or a SAN or new cloud storage mechanisms like EBS and S3 and things like that. I think this is a good place to think about encryption, right? Especially if you're going onto the cloud. We hear all the time now about S3 buckets getting exposed and the data is in clear text. We also have EBS volumes that are getting, for some reason, shared out to the world where anybody can go and download and view them. If you're enabling encryption at those levels, it's just like another layer of protection against some sort of misconfiguration. So finally, we've got transport layer encryption. And the main threats against this are basically your network level threats, right? So somebody's man-in-the-milling you, some nefarious countries hijacking BGP routes, things like that. And basically, I don't know any reason why you wouldn't do the encryption in all these different layers, especially when there's such nice new services out here like Let's Encrypt and the Mozilla SSL configuration generator. So has anybody actually used either Let's Encrypt or the Mozilla tool? Sweet. I like the Mozilla tool quite a bit. That's actually what Let's Encrypt uses as its preferred Cypher suite list. So if you're curious like why it chooses what it chooses, it comes from Mozilla. It also gives a lot of different options as far as like what your web server is, how strong you want to make it, or aggressive, I might say. They have modern settings, intermediate, and old. One of the things that you may want to consider is look at like what sort of end browsers are connecting to your services and seeing what you may need to support. You might be surprised how many XP machines are connecting to your system. We were when we first started analyzing this a few years ago, and we started putting notices anytime we saw browsers that were too old to say, hey, like for your own security, you should be looking at upgrading your system, and then we eventually blocked access to anything that was too old. All right, so now we're going to get into some fun code stuff. So I'll try to make this as large as I can, and let me know if I can. How does that look? Probably can't read much, huh? Nope. Okay. Let's see where I can zoom in here. That's weird. There we go.
Can you speak a little louder?
Sure.
Thank you.
Sure. All right. So here's something we're going to take a look at. This comes from this is JavaScript code, so it comes from an application that we're working on internally. It's got a number of different flaws with it, and I'll try to walk through some of this. It might be a little bit hard here, just because we're trying to blow this up. And this was a case where they were doing pretty good stuff, right? And there's a couple of little things here that tripped them up that ultimately really sort of, I don't say killed the encryption, but it definitely hurt it in ways that attackers could take advantage of. And so, let's see here. So the first thing we're going to take a look at is this little guy right here. So first thing we have is a static salt. So hard-coded into this application is a salt. So salts are generally something that you want to have unique for each encryption operation that you're doing. So in this case, they were hard-coding salt, and it would be the same for any time that they generated the key here. So this is a key generation algorithm. So you definitely, when you're going to build encryption stuff, salts are something that they're not secret, but they're used to make sure that the same decryption operation is not the same every time you go to do the decryption. The next thing in this piece of code is we're looking at PBKDF2. So that's a password-based key derivation function. So imagine it's going to take something like a fast hashing algorithm. In this case, it's HMAC SHA-256, and it's going to run it a bunch of times, right, to make it a lot harder to try to gain access to that plain text. So in this case, it's going to run it 4,000 times. And I'm not going to say this is bad. And PBKDF2 is kind of interesting, where you generally have to use it to tune it. So a good example of that is if you go read some white papers from like Apple on how they do iOS, they used to use PBKDF2 and they would tune it to a certain user experience. I think it was 80 milliseconds they wanted the login to be when they actually ran through this. So they would run it for different iterations on different phone models, right? So as processors got faster, they would actually increase the number of iterations so it stayed the same user experience, but they were actually getting better and better security as the phones were able to process faster. So this would be something I would maybe like investigate to see, is this an acceptable user experience? Could you double this? Could you triple this sort of deal to make it that much harder to recover that plain text? All right, so the next two here we're basically logging the key material. So this is a no-no, right? So we're doing pretty good. We get to here, and now we're actually taking the results of the different crypto operations and we're writing it to disk. So this is obviously like not good, right? So easy fix, delete the 2 lines, move on. But again, you should never, dump this stuff out to a log file. Now here's where things kind of start to get weird. So for some reason in this implementation, this is just odd to me, that they're using 2 different PBKDF2 functions from 2 different libraries. It's not really a security flaw, just kind of a weird coding thing that probably for like code clarity, you should probably use the same function. Not necessarily a security thing, but just indicates that like maybe we copy and pasted from Stack Overflow and probably should use some extra some extra scrutiny on this code. So now we're going to get to a little bit trickier things. So has anybody heard of CryptoPals? So a handful of people. So if you're interested in cryptography and how to actually break it, I highly recommend you go out to, I think it's cryptopals.com. I've got links at the end of the deck. But basically it's a whole bunch of challenges. I think 8 sets of challenges. There's like 64 in total. But they actually walk you through how to build and break different crypto systems. So you actually build your own AES systems. You'll build ECB and see how bad that is and how you can break that. And one of the interesting rules that I learned from that was to always operate on raw bytes and not on strings, because weird things can happen when you start messing with strings instead of bytes. And so we have it in 2 places here. Let's zoom in so maybe we can see it. So in the first case here, we've got our hash value here, which came from our first PBK2DF function. And now we're doing a 2-string on that. So it's taking the value of that and putting it into some hex notation. And for the second one, we're doing some really goofy stuff here. So .join. Does anybody know what a .join does in JavaScript? So yeah, so it'll convert like say an array structure to a string, and then it uses whatever characters in that you provided as like a delimiter in between those. So in this case, it's taking whatever was there, making it a string, and then joining it by spaces. So the weird thing here is we were doing pretty good, even ignoring that first 2-string function. We then convert this from a nice bit array that has full key scope to a string that only has digits, spaces, and potentially minus signs if it's a negative integer, signed integer. So literally we're changing the value of this. It's not even the original key that would have generated coming out of here. And I didn't do the math for this particular one, but it definitely cuts down on the overall key space here. So what I've learned is like the only really good way to review crypto stuff is actually look at the code, and I will usually break down each line of code and understand like what is it doing, what sort of weird operations might be happening here, especially when we start doing string manipulation things, like things go right like really quickly. So I guess that's it for that one. You know, the ways to sort of fix this, obviously we talked about the salts, right? Like generate a new salt every time. They're not meant to be secret. You can store it with the encrypted data. That's fine. Don't use strings. Operate on the bytes or bit arrays. And that's probably the biggest ways to fix this. And I believe that's what we end up doing to actually fix this before it went to production.
It's the same salt. It's going to generate the same crypto string, crypto text every time you encrypt the same thing.
If the key is the same as well, or the password in the case of PBKDF2. So zoom in. So like in PBKDF2, you've got, well, we have PWD here. It's meant to be a password, right, or some sort of string. That's what's going to change what the output is, right, along with the salt and the iterations, and ultimately the key size is what you're returning from that.
But if it's the same password, because it's the same salt, it's going to generate the same cryptographic
Right.
string.
Yep.
It's much easier to do for us.
Right. Right. Yeah, so the comment was if it's the same salt and you put the same password in, it's going to generate the same hash, which is exactly right. You know, so imagine if you're using this in a very large database with lots and lots of users, and people choose really terrible passwords, as we've seen by so many password breaches that were released, you're going to see lots of the same strings over and over and over again. Yep. All right, so we're going to do a little bit on randomness. So we're not going to go too deep into this, and this is a little bit easier to get through than the other one. This is actually some code prior to us launching an open source project. We do some reviews on things. We launched an open source project called Canali, which is a API gateway for Kubernetes clusters. This was a utility that was used to generate API keys to put into that API gateway. So this is written in Go. So some of the couple interesting things here are that first it's using math.rand. I would say general rule of thumb is anytime you see math.rand, it's probably not suitable for actual crypto use. Usually there's a separate crypto library. Use that if you're using anything if you're trying to do crypto stuff, right? Don't use the math random because these are deterministic. And what I mean by that is if you put in, say, 1 or 0 in this math.rand and you ran this 2 times in a row, you will get the same result, right? So it's literally, there's a algorithm to create pseudo-random numbers, but it's predictable if you know what this is. So in this case, the developer put in here use a timestamp, right? And it goes down to the nanosecond. However, knowing roughly when they created this, right? Because especially this is up in GitHub now, and we know, say the developer created keys around the same time as they deploy their apps, right? And they push their projects. You can start to zero in on what that time would be and massively narrow down what the potential is for the key that gets generated from here. So always use crypto random and not like math random. And here's where we get some kind of crazy stuff, right? So we're going to look at the sort of the rest of the code here and try to make sense of this. So what you might notice at the front of this is that we've got a couple of constants here. One is the name of the tool, right? And the other is this character array here. So we've got lowercase, uppercase, and some digits. And so one of the things that if you get into like cryptography and you start to look at that, One of the things you know is like this is a pretty small key space. There's 62 values here, which makes that much smaller than, say, a full 256 bytes that would be possible if you use unprintable characters. Probably because the developer didn't know how to convert, say, unprintable characters into printable using hex, encoding and things like that, or base64, where the case might have been. They chose to do this, and using the math_ran function that we looked at earlier, basically randomizes and grabs a character from that list up to whatever number of bytes that they requested. So I think it was 32 different characters, right? And then from there, it would generate a random string of 32 characters. So the problem with this is you're severely limiting the character space. So I did a little bit of math on this, and hopefully it's right. So if we have 32 characters here, and you have 62 possibilities per character, you've got 2 times 10 to the 93rd, which is a pretty big number. Literally 93 zeros on something, right? That's pretty big. If you do it the actual cryptographic way, where you use the full key space for that, you actually get 1.9 times 10 to the 308th, right? So there's a difference of basically 214 zeros on the end of something, right? Is the difference between like using 62 characters here and the full 256 bits that would have been available had he chose the actual crypto random piece. So just a little bit of difference. Especially that he's using a deterministic math function to seed it, right? So now you can understand, like, we went from what could have been a really, really large number down to something that is predictable, and we're even crippling it further by using a limited key space. So now here's the time for the comedy bug of the day. So a shout out goes out to our MadSec friends. Pork specifically posted this a few weeks back in our Slack channel. And I looked at this and immediately knew this was terrible. And so we'll do it a little bit here. Oops, jump ahead. And so I'm not sure exactly what this goes to. He said some sort of consumer device, think like a Linksys or something like that. I think they're doing some sort of a review of this. He's got a few bugs into the vendor. But again, sort of like we saw before, this doesn't look good. Here's a list of possible characters, right? So I'm thinking it's something kind of like that one we looked at before. But then as I'm scrolling through here, I don't see any actual crypto functions. The only thing I see is math.floor, which is going to generate some random number. There's no crypto here. This is some sort of like weird encoding. So if you take a look here, it's doing some modulo stuff. So mod 7, so every 7th character, it's going to do something. And it looks like it grabs the last character of whatever you pass into it, and then appends it to this text. And ultimately, text is what gets returned. And for the rest of the characters, it's just grabbing, again, a random character. And so what this actually does is when you put in some value like this, like all A's, you end up with this thing. So the red is the actual password. It doesn't encrypt it. It just puts it every 7th position and reverses it, right? So it'd be your password backwards, put in every 7th position, and then it's a little bit hard to see, but like the orange numbers up here are actually the length of it. So the first one here is a 0, meaning that it's not over 10 characters, and the other one is the actual length of 6. So it uses the modulus to say what's the length of anything under 10. This has to be way more work than actually doing it correctly. Like, come on, go to GitHub, download one of the 2 libraries where you looked at for JavaScript, implement that, and then send it correctly. I don't know why they were doing this, and it sounds like there may be bugs associated with this, as he was playing with it earlier. So one of the last sections we're going to talk about is key management. So I'm not going to go into too much depth about this, because this literally could be like an entire topic in itself. But secrets should never be stored in plain text, right? Especially in repositories, especially on like GitHub or Bitbucket or anything like that, right? One of the things that I think would really help people. SharePoint? Ooh, that's a good one. I like that. Yeah. SharePoint is totally secure. Yes. I think really having like a strategy before you start implementing something is probably the best way to go about it. And frankly, like use something that resembles like a vaulting solution. Kind of matters, but at the same time, like it's better than like sticking stuff in repositories directly or hard coding stuff in applications. Somebody gets access to the application through some means because you're not doing like disk encryption or if you have like an EBS volume for some reason that you expose out to the world. I don't know why you do that, but people seem to do that. Now your keys get exposed and people gain access to your applications. Rotate your keys for similar reasons that you rotate passwords. People leave, things like that. And seriously, just look at a vaulting solution. So there's a number of them out there. It depends on your context, what sort of application you're trying to develop. There's different things out there. Hardware security module has been the typical go-to for years for doing sensitive encryption type things. That's still a great way to go. It may not scale or it may not fit your model. Like if you're going to the cloud, there are some options for doing that, but it may not scale across regions or multiple facilities. You can look to things like Amazon KMS and Azure Key Vault. There's newer open source ones that are coming out as well, like Conjure and Ansible Vault that can also do better than sticking things directly into plain text files. So regardless of like what you go with, please just go with something. I also learned recently that you can't search across GitHub like you could anymore looking for those keys. It makes it a little bit better that people aren't shooting themselves in the foot as much, but still, don't just stick them in repositories. So here's kind of the summary of like the general recommendations. So build a threat model of your application. This is just going to help inform you of like where should you be looking at, like what sort of areas are going to benefit the most from encryption, and use that model to inform your cryptographic choices. So, whether that's in transport or that's on disk or in the application, like you'll be able to figure out what makes most sense for you, and implement those appropriate crypto choices from the cryptographic right answers. Like I highly recommend that document. It's pretty good. There's a number of different options within that document, so it's not just just use this CypherSuite because it's the best one. It says, well, use this is the best. If you can't use that, maybe use this one, and then gives you a few different options for how you actually do the encryption pieces. Design proper key management in from the beginning as part of the implementation. Otherwise, you end up with systems that when it comes time to do key rotation, you're like, crap, how do I do that? Or it's going to be awful. So have that thought up front, because most places that require the encryption will require you to do the rotation anyway, whether that's compliance or just good security practice. And use a CSPRNG, not math random. Anytime you need to generate a random number. And please don't try to roll your own, because that doesn't work very well either. Also, always operate on raw bytes and not strings. And profit. So, a few different references, and I'll post in the slides later. But there's the cryptographic right answers, how to safely generate random numbers, the crypto pals challenges if you want to get into like actually playing with the crypto and trying to break it. There's a great new book out called Serious Crypto that is from No Starch, and it gets pretty deep into some of the math, but also has some really good points about like how to attack it and what are some of the pitfalls of the different approaches, whether it's hashing or stream ciphers or whatever sort of encryption they're talking about. And also Mozilla's server-side encryption tool is really handy for generating those configs, as well as Let's Encrypt for generating certificates for you. So
I've seen that AES ECB picture thing before, but I'm curious how, given a standard like that was vetted by crypto people and everything, like how could something that blatantly bad come out of that? And like, what's the story behind that? And what should we use? What part of AES should we use, I guess?
Sure, it's a good question. So question is around, the picture of the dog on fire, right? That's encrypted with AES ECB. How did that get to be the way it was? I'm not sure. It's basically easy mode AES, right? So it doesn't take in a IV. So which is why you see what you see. That's like the biggest cause of it. It also doesn't chain blocks together like you would see in like a block chaining version. And so sort of those two things together cause that issue. It was the first, I think, mode that came out. It's also like the easiest mode to implement because you don't have to do salts, right? Or not salts, initialization vectors. And that's basically it. So one of the other things I've noticed too is, unfortunately, a lot of like the newer libraries that come out will say, hey, this is all you have to do encryption, right? And it's just doing AES ECB under the hood. Like the newer JavaScript ones are just say, hey, literally like here's a line, you put in like your key, and then here's your data, and then it spits out like the ciphertext. And unfortunately, you end up with things like that. So you have to sort of read the documentation, understand what's happening under the hood. But yeah, the general issue is that there's no initialization vector, and then nothing's chained, and so you'll end up with blocks that are the same for the same plain text.
What client-side crypto library do you see the most? Is it Crypto.js or is there some other ones?
I think there's a number of them. Yeah, I think Crypto.js is probably the most popular. There's the Stanford one that's pretty good too, but I don't. Either of those, I don't know if there's an actual standard or preferred one. Either of those I think do pretty well.
Okay.
Familiar with Crypto Swift for iOS?
I haven't heard that. Not too much of this. Cool. All right. Well, thank you. I'm getting we're all done signed, so thank you very much. Questions, I'll be at Lockwood and Village.